So, we continue with the discussion on the blocking and non-blocking assignments. So, in this lecture we shall be looking at some more differences in the way they behave and the way the synthesis or the simulation tool will interpret or handle the description that we have given or provided in either blocking or non-blocking kind of assignments. Okay. So, we shall be illustrating these points through a number of examples. That will be the best way to just explain. So, actually through the examples we shall be showing you some modeling styles, using both blocking assignment and also using non-blocking assignments. And there we will try to understand by looking at the semantics or the meaning of those statements, how the simulator or the synthesis tool might be influenced to capture the behavior of a model in a particular way, that whether it is actually capturing the behavior in the way you are intending or it is doing something else. Okay. So, as these are something which is extremely important from the point of view of the designer, because you have to understand this blocking and non-blocking statements very clearly, because if you do not model the behavior of your circuit or system that you want to in the proper way, then even a very small error in the model which might easily be overlooked, that might result in a drastically different output or a drastically different circuit, depending on whether you are simulating or synthesizing. Okay. So, we shall be trying to see some examples. Now, there is another thing I mentioned repeatedly, that when you are studying some codes, when you are learning some constructs of a language, so it is always recommended that you actually run the code. Say for Verilog you simulate it and see how the outputs are coming, change the code and see what are the changes that are happening. Okay. Okay. So, the first example that I take is a simple timed assignment using blocking and non-blocking, a very simple segment of code. So, inside a block, begin and block, this can be inside either always or initial, whatever, some procedural block. I write blocking assignment after delay of 5 b, c equal to after delay of 5 a, and here similar, but non-blocking. So, let us try to understand what will happen here. Blocking statements will be executing one after the other. First statement will say that after a time delay of 5, b will be assigned to a. Second statement says after this is finished, only then it will come to the second statement. So, after another time delay of 5, that value of a will be copied to c. So, the value of b which was there, it first goes to a and then it goes to c. So, the value of b will be finally assigned to c after a delay of 10 time units, right. This will happen here. Now, if you use a non-blocking assignment statement, what will this mean? This will mean here the time delay does not mean that you first finish this after time 5, then again after time 5 do this. No, it will mean that you evaluate the right hand sides. See, a is scheduled to get the value of b 5 time units into the future. Right hand sides are evaluated together, and when you say #5 and #5, it does not mean like this, that first this 5 and then this 5, this is actually 10, not this. Both of these are waiting for time 5 and they are assigning, they are executing concurrently, right. So, here b will be assigned after time 5 to a will be also assigned after time 5 to c. So, you see in the first case here the value of B was assigned to C, but here finally the value of A will get assigned to C, right. So, the final value of C will be different for these two cases. This is a very simple example, but you will have to understand the difference very clearly, what this hash 5 here and what this hash 5 here means. So, when you are using a blocking assignment, I am repeating, if you are using those delays, because in a blocking assignment statement, the statements will be executed one after the other, the delays will get accumulated. If you give 5, 5, 5, it will be 5, 10, 15, 20, that way the delays will get accumulated. But in a non-blocking case, it is not so. There the delay means you evaluate all the right hand sides together, and after how much time you will be assigning it to the left hand side. If you give all then hash 5, hash 5, hash 5, means after delay of 5, all of them will be assigned together. It is not that the delays will be adding up, not like that. Okay? So, because of that, for these two cases the final value of C was coming to be different. Let us take another example. This is a procedural block with a clock, always POSIX clock. Here I am using a blocking assignment. So, what does this block mean? This block means that whenever there is a positive edge of the clock, you activate or start executing this. What is this saying? That you first assign A to Q1, then assign Q1 to Q2, right. So, in terms of the hardware, if you give it to the synthesis tool, what synthesis tool it will generate? You see, A is assigned to Q1. Just think, a flip flop, A will be assigned to Q1. So, whenever the positive edge of the clock comes, A will be assigned to Q1, it will be stored in the D flip flop. The first statement goes, and after this is done, this Q1 will be assigned to Q2, because you see this is not that Q1 will be connected to this, because you will have to understand what is the meaning of non-blocking. The synthesis tool and also the simulation tool, they know what is the meaning of the blocking assignments. Blocking assignment means the statements are supposed to be executed one after the other. After the first statement executes, that value will be used to execute the second statement one by one sequentially. Okay? So, if you keep that sequential thing in mind, then you see the first statement says Q1 equal to A. This is fine, it will be mapped to this flip flop, Q1 will be A, but after this is completed, only then the second one will start. So, this Q1 already has received the value of A. So, that A is supposed to go to Q2. Okay? So, the synthesis tool will understand that meaning of this blocking assignment. So, instead of connecting Q1, it will connect A directly to the second flip flop also to generate Q. So, it will be two parallel flip flops. After the clock, finally, both Q1 and Q2 will be getting the same value A. A will be stored here as well as A will be stored here, as this meaning shows. This A will go to Q1, Q1 will go to Q2, same A will come, right. So, in terms of the hardware, it will be two parallel flip flops. Let us look at a slightly different. You see, this was my description. I simply interchange the order. I just write it like this, and below I write an description, same description using non-blocking assignment. Here let us try to understand what will happen. Here we have written Q2 equal to Q1 and Q1 equal to A. What does this mean? You see, you can imagine there will be two flip flops. Q1 will be the output of one of the flip flops, Q2 will be the output of the other flip flop. First one you are saying that Q1 will be going to Q2, which means this Q1 has to be connected to the input of this, Q1 will have to go to Q2. Secondary we are saying some other variable, because after this is completed only then you will come here, A will go to Q1. So, some other value A will go to Q1. So, the old value of Q1 will go to Q2, this A will be going to Q1. You see what we are trying to say is nothing but a shift register. If you write it in the other way around by interchanging the order, what you are saying is just a 2-bit shift register. Q1 will be shifting to Q2 and this A will be shifting into Q1. Right. So, the same thing will happen for the non-blocking case also. Non-blocking means the same thing, Q1 will go to Q2, A will go to Q1. The order is not important, because in whatever way you just order you mention. So, the hardware that will be synthesized will be a 2-bit shift register. Q1 will go to Q2, A will go to Q1. So, here also A goes to Q1, A goes to Q1, Q1 goes to Q2, Q1 goes to Q2. So, the previous values of A and Q1, previous value of A, previous value of Q1, they will be assigned to Q1 and Q2. This will be assigned to Q1, previous value of Q1 will be assigned to Q2. So, both of these descriptions model a shift register. So, one thing you understand, for a blocking case it is very peculiar. So, if you write the two statements in a particular order, then it will generate two flip flops in parallel, but if you simply interchange them, it will become a shift register. So, this you will be able to understand only if you know what is the meaning of the blocking assignments. If there are some statements, what exactly is the meaning and how they will execute and what will be the final result, right. Okay. So, let us continue. Let us take another example. Here there are two blocks, two procedural blocks, both on positive edge. Here you are saying at the positive edge Q1 will go to Q2, also the positive edge A will go to Q1. Just if you move back in the previous slide, you see here we used a single procedural block, but you are doing the same thing. At the positive edge A was going to Q1, Q1 was going to Q2. But here we are meaning the same thing, maybe we are using two different blocks, but both are activating in positive edge and the assignment will take place in a very similar way. So, here also you will be generating the same shift register, right. So, this is fairly simple. So, if you just put them in this order, then also you can generate a shift register. But if you put them the same code, instead of non-blocking, if you put blocking, what will happen? Let us understand. Here there are two different always blocks. So, in the earlier case we said that the two statements were inside a single always block, which means they were executing one after the other. But here I am saying there are two different always blocks, they are executing concurrently. Maybe there are blocking assignments, but Q1 equal to A and Q2 equal to Q1, both will be executing together whenever pause edge of the clock comes. So, now you see what will happen. Well, Q1 will go to Q2 is fine, but A will be going to Q1. Now, in terms of the hardware, just see. So, what we are trying to say is this: first statement says A will go to Q1, that means A will go to Q1. Second statement says Q1 will go to Q2. So, some Q1 will go to Q2, both at the positive edge, but the value of Q2 will be indeterminate, because what will be this Q1 here? Will it be the old value of Q1 or this new value of Q1 which you have just now loaded into Q1 from A? This description is a little ambiguous. If we use blocking statements here, this description is ambiguous and you should avoid this, because simulator may also confuse this Q2 will become indeterminate. because if the simulator first executes this. So, whatever was the old value of q 1, it will be assigned to q 2, then a will be assigned to q 1, but if it executes this first, then the new value of a 1 will be assigned to q 1 and that q 1 will be assigned to q 2. So, it will act as a shift register. So, the interpretation of the meaning may not be unique depending on the order of the execution that will be scheduled by the simulator. Okay. The synthesis tool will also give you a warning that there is a confusion and the output value will be indeterminate. So, you should, the crux is that you should try to avoid clock triggered assignment on blocking statement as far as possible. Whenever you want to carry out assignment with clock triggering, better to use non blocking, then all these problems will not occur. Okay? Fine. Let us look at another example which is slightly more complex and little bigger. Well, here our objective was to design a 4-bit shift register. Suppose this was what we started to design. So, we wanted to design a 4-bit shift register like this. There are 4 flip flops. The output of one flip flop will go to the input of the second flip flop. So, this is what we are trying to model, let us say, and of course, there will be a clock, there will be a clock signal which will be feeding in parallel to all the flip flops, and of course, there will also be a clear input. Clear will be active 0. So, whenever it is 0, it is activated. So, I am showing it as a bubble. Suppose this is what I was trying to model, and let us say we came up with a Verilog code like this. Let us see whether this Verilog code means actually models a shift register like this or not, right. Let us see. Here, as I said, our parameters are clock, clear, A and E. So, what is our A and what is our E? This E is our input and A is our output. You see, A is the input and E is the output. Fine. E is the input and A is the output. So, actually what we want here is that, let us say, we want a shift register where we wanted to call these as E, we wanted to call this A, and the intermediate point let us call this as B, C and D. So, you can either do it like this or you can do it in the previous way, that will be easier. I think let us keep it in the previous way, that will be easier. Let us call this E, let us call this A, then this will be B, this will be C, this will be D. So, it really does not matter. Keep it. So, let us just revert back in the previous one. Let us see. So, here the intermediate points B, C, D we are declaring as reg. Now, in the block what we are doing, we are saying always at positive edge clock or negative edge clear. So, whenever either there is a clock going high or a clear is becoming 0, you enter this block. If clear is 0, if not clear, in this beginning block you clear B, C, D, E to zeros. So, there are two, so here there are 4 flip flops B, C, D, E, you initialize them to all 0, 0, 0, 0, 0. So, whenever clear is 1, clear is 0, not clear is 1. Okay. Else clock has come, you are trying to do something, you are writing 4 things, you are writing E equal to D, you are writing D equal to C, you are writing C equal to B and you are writing B equal to A. So, if you write like the what is meaning? D equal to E means whatever is D you are copying to E, D equal to C. So, whatever is C you are copying to D, C equal to B, whatever in B you are copying to C, whatever in B, B you are A you are copying to B, right. So, this is like the shift register thing. So, this is the shift register which will be trying to model like this, right. And this is the description. E equal to D means, so in this order the statements will be executed. These are all blocking assignments. First D will be assigned to E. So, in a shift register what happens? Suppose in shift register my bits were 0, 1, 0, 1. Now, if I apply a clock, what will happen? A clock comes. This will be shifted, right. So, this 0 will come here, this 1 will come here, this 0 will come here, this 1 will come out and a new 0 will come in. So, you see D equal to E, this is E, this is D, this is C, this is B. D equal to E, whatever was D, this goes to E. This is the first step. Then C goes to D, whatever is C it goes to D, then B goes to C, whatever is B it goes to C, then A is the input, okay. A is the input from outside, A goes to B. So, A goes to B. So, it is actually shift register, first you are shifting this, then you are shifting this, then you are shifting this, then you are shifting this. This is correct behavior of a shift register. So, when you are actually trying to model a shift register, this order is correct. So, I think here let us correct this, this actually A should be input and this E should be output. This is correct description. Okay. This A is input and E is output, this is correct, fine. So, this is a correct way of modeling a shift register like this. Now, suppose we make a small change, just this four assignments which are there, we simply reverse their order. We just write B equal to A first, C equal to B next, D equal to C next and E equal to D last. So, we just reverse the order of the procedural assignments, the remaining thing is unchanged, just these 4 statements we reversed. See, ultimately you may think that well we are actually trying to do a shift register. So, whether you specify that first and then this or this first and then this should be the same, it should not matter. But suppose you do it like this, then what will happen? Let us see. Well, this A is coming from outside, right? A is the external input which is coming here. Now, you are first saying A equal B equal to A. So, whatever is A, that is first coming to B. So, A, suppose the value of A was x, let us say. So, x will come here, then this statement will execute, B is going to C. So, B is already got x, that x will go to C, this x will go to C, then D equal to C, C is got x, x will go to D, x will go to D, E equal to D, that x will go to E. So, whatever was the value of A is directly going to E. So, it is not exactly like a shift register it is working, because the earlier case it was not so. The previous value of D was going to E, then C was going to D, then B was going to C, then A was going to B. So, A was not overwriting everything. So, if I change the order, whatever new value I have applied to A, that will be overwriting B, then C, then D, then E, all of them will become x. So, actually the synthesis tool will also do this analysis and it will find out, well, actually what you are meaning is d equal to a. See, the synthesis tool, whatever you specify, it will always try to do some optimization. If you specify a function, it will do some minimization and try to get the best circuit. Here also you have provided some specification, but the tool does some analysis and finds that, well, what you mean is actually d equal to a, right. So, instead of a shift register, what it will be generating is nothing but a single flip flop, means E equal to, not D equal to, E equal to, final E. So, the A will be going directly to E. So, the intermediate things are not generated. So, although you might have wanted a shift register to be generated, but the synthesis tool had applied some intelligence and found out that the way you have specified using blocking statements, it is not really a shift register specification. You are directly just assigning the input to the final output. So, it will be generating a single flip flop, right. So, whatever I have said is mentioned here. Effect of assignment, A goes to B, B goes to C, C goes to D, D goes to E. So, because they are executed sequentially, the final result is A will be going to E. So, synthesis tool will be generating a single flip flop like this, right. So, see, if you had done the same thing using non-blocking assignments, then irrespective of the order in which you give the statements, it will still be a shift register. These 4 statements you can do any permutation. You can bring the first statement third, last statement first, any order you specify, but the meaning is same. All the right hand sides will be evaluated at the same time, read, and they will be assigned at the same time. So, the shifting will be shifting. It will not matter means on in which order you are just putting or writing those statements in the block. So, here if you are using non-blocking statements, the statements can appear in any order, still it will be a shift register. So, as you can see, as I mentioned earlier, that for this kind of clocked sequential circuits, non-blocking assignment is a much safer option, because here this is one big example, that even if you just interchange these lines by mistake, still your final circuit will be a shift register, it will not change. It will be a right hand side expressions are evaluated all in parallel. Because they are evaluated in parallel, the order is not important. D will finally go to E, C will finally go to D, and so on. The old values will go to this. It does not depend on the order in which put the statements. So, it will generate a shift register like this. So, this is what I am emphasizing repeatedly, that whenever you are modeling a synchronous sequential circuit, it is always a very good practice to use non-blocking assignments, so that the errors like the one I tried to highlight can be avoided. Okay. So, with this we come to the end of this lecture. Thank you.